All right, we are on the last section, section 5.8, forces of friction. Uh, so let's read the little caption above the trash can. For small applied forces, the magnitude of the force of static friction equals the magnitude of the applied force. So if you apply more force, will there be more friction? Yes. The force of friction is it's related to how much force it is up to a certain point. Then we move from static friction to kinetic friction. But we'll get into that in a bit. So when an object is in motion on a surface or in a viscous medium such as air and water, there is resistance to the motion because the object interacts with its surroundings. This resistance is called the force of friction. Friction is important. It allows us to walk or run, and it's necessary for motion of wheeled vehicles. I mean, if you've ever skidded on a rainy slick surface, you've lost friction, and it doesn't feel nice. I'll try to post a video of some mobility denial system that we developed at Southwest Research that shows how important friction is. Imagine dragging a full trash can across a rough surface. Apply external horizontal force F to the right. The can remains stationary when F is small. The force that counteracts F, the force, and keeps it from moving, acts toward the left, the force of static friction, F sub S. As long as the trash can is not moving, F of S equals F. So you apply a small force, the force of static friction is small. If you apply a larger force, as long as it's not moving, the force of static friction will increase. If it's not moving, then the sum of the forces has to equal 0. So F sub S will equal F in the opposite direction until it moves. So if F increases, F sub S also increases. If F decreases, F sub S also decreases. Friction forces arise from the nature of the two surfaces. Because of their roughness, contact made only at a few locations where peaks of materials touch. At these locations, friction force arises because one peak physically blocks motion of the peak from the opposing surface. Chemical bonding, spot welds of opposing peaks as they come into contact. There is chemical bonding of the opposing peaks. Details of friction is quite complex at atomic level. The force ultimately involves electrical interaction between atoms or molecules. Now, let's see what happens when you increase. So if you look at well, first let's read the bubble. When the magnitude of the applied force exceeds the magnitude of the maximum force of static friction, the trash can breaks free and accelerates to the right. So look at that static region. It's a straight line from 0 to the max static friction. So if you apply a little force, you get a little F sub S, static friction. You apply more, you get more static friction, all the way to where it breaks. And so let's see what's happening. You increase the magnitude of F in the left figure, the trash can eventually slip. When the trash can is on the verge of slipping, F sub S is at its maximum value. When the force exceeds F sub S max, the trash can move and accelerates to the right. The friction force for the object in motion is the force of kinetic friction, F sub K. So there's F sub S, static friction, and F sub K, kinetic friction. When the trash can is in motion, the force of the kinetic friction is less than the force of static friction max. The net force, F minus F sub K in the x direction, produces acceleration to the right. That's Newton's second law. If F equals F sub k, the acceleration is equal to 0. The trash can moves to the right with a constant speed. If the applied force F is removed, the friction force F sub k provides acceleration of the trash can in the x direction. Eventually, it brings it to a rest. The friction brings it to a rest. If you take off your foot off the accelerator pedal in your car, it'll come to a halt, not only because of the friction between the road and the tires, but also because of all the internal parts that are moving. That friction will slow your car down if you take your foot off the accelerator pedal. Now let's look at. Let's make sure. Yeah, okay, I finished that slide. Here we have coefficients of friction, rubber on concrete, and you'll notice in these, I think without exception, the static friction, the coefficient of static friction, is always greater than the coefficient of kinetic friction. The only time it seems to be they're equal is Teflon on Teflon if you look at the slides, but in every other case it's the coefficient of static friction is greater than the coefficient of kinetic friction. Experimentally, to a good approximation, both the force of static friction max and the force of kinetic friction are proportional to the magnitude of the normal force exerted on the object by the surface. Simplification model for forces of friction based on experiments, the magnitude of the static friction force between any two surfaces in contact, it's dimensionless. It's dimensionless. So the force of static friction is less than or equal to mu sub s times n, where n is the normal. In other words, the normal is going to equal mg. So the n, the larger the m, the larger the normal. So the f of s is going to be less than or equal to mu sub s times the normal, which the normal is mg. There's a dimensionless constant. Mu sub s is the coefficient of static friction, and is the magnitude of the normal force exerted by one surface on another. Equality holds when the surfaces are on the verge of slipping. That is, when this is the case, the F of static friction is equal to Fs max equals mu sub s times n. Now, the magnitude of the force of kinetic friction acting on two surfaces is shown here. The force of kinetic friction equals mu sub k times the normal force. Mu sub k is the coefficient of kinetic friction. Coefficient of kinetic friction can vary with speed. We usually neglect that. Values of mu sub k and mu sub s depend on the nature of the surfaces. Generally, as I said earlier, mu sub k is less than mu sub s. Typical values are anywhere from 0.03 to 1. Okay, the direction of friction of the friction force is parallel to the surface and opposite the actual motion for kinetic friction, or impending motion, the static friction of the object relative to the surface. For static friction, it's always opposite the applied force. So the coefficients of friction are nearly independent of the area of contact between the surfaces. You might expect that placing an object on the side having the most area might increase the friction force, since it provides more points in contact. But the weight is spread out over a larger area and individual points are not pressed together as tightly. The effects approximately compensate. So the friction force is independent of area. That seems counterintuitive, but it is. Let's look at an example. You press your physics textbook flat against a vertical wall with your hand. What is the direction of the friction force exerted by the wall on the book. What is the friction force? Is it downward, upward, out from the wall, or into the wall? Well, it's upward. If you're pushing against the wall, gravity is the force that's making your book want to go downward. Well, if the gravitational force is downward, the friction force is upward. So it's upward. All right, now let's look at another one. Charlie is playing with his daughter Tori in the snow. She sits on a sled and asks him to slide her across a flat horizontal field. Charlie has a choice of A, pushing her from behind by applying a force downward on her shoulders at 30 degrees below the horizontal, or attaching a rope to the front of the sled and pulling with a force at 30 degrees above the horizontal. Which would be easier for him and why? Which would be easier for him and why? Oops, I'm sorry. There's the problem. I apologize. Charlie is playing with his daughter Tori in the snow. She sits on a sled and asks him to slide her across a flat horizontal field. Charlie has a choice. Push downward 30 degrees or pull upward. What do you think would be easier? Well, if he's pushing down on her, he's exerting, just like you push the physics book against the wall, you're putting more pressure and applying more greater. So there's a normal component. If he pushes down on her, there's a normal component that is exerted upward. But if he's pulling, he's reducing that normal component. So the answer is B, attaching a rope to the front of the sled and pulling with a force 30 degrees up. When pulling with the rope, there's a component of your applied force that is upward, which reduces the normal force between the sled and the snow. In turn, the friction force between the sled and the snow is reduced, making the sled easier to move. If you push from behind with a force with a downward component, the normal force is larger, the friction force is larger, and the sled is harder to move. All right, let's look at that was a quick quiz. Let's look at an example. The following is a simple method of measuring coefficients of friction. We're actually going to do this when we get to the friction lab. The following is a simple method of measuring coefficients of friction. Suppose a block is placed on a rough surface inclined relative to the horizontal as shown in the figure. The incline angle is increased until the block starts to move, so that you can obtain mu sub s by measuring the critical angle theta sub c at which this slipping just occurs. Now let's look at this for a little bit. You've got mg sine theta and mg cosine theta. The downward force is mg sine theta, and the f sub s is opposite that, and it's mu sub s times the normal. Okay, well let's take a closer look, and we're going to end up seeing that the mu sub s is the tangent of theta, and we'll see why. To conceptualize this, let's consider the figure and imagine that the block tends to slide down the incline due to the gravitational force. To simulate this situation, place a coin on a book's cover and tilt the book until the coin begins to slide. Notice how this example differs than if there were no friction. When there's no friction on an incline, any angle of the incline will cause a stationary object to begin moving. When there is friction, however, there is no movement of the object for angles less than the critical angle. Let's categorize this as follows. The block is subject to various forces. Because we are raising the plane to the angle at which the block is just ready to begin to move, but is not moving, we categorize the block as a particle in equilibrium. Okay? Now let's analyze this as follows. The diagram shows the forces on the block, the gravitational force mg, the normal force n, and the force of static friction F sub s. We choose x to be parallel to the plane and y perpendicular to it. From the particle in equilibrium model applies the sum of the forces equals 0 to the block in both the x and y directions. So we have the sum of the forces in the x direction, or mg sine theta, minus the static friction, and they have to equal 0 if there is no motion. The sum of the forces in the y direction, or the normal force, minus the mg cosine theta, they equal 0. Okay. Now let's substitute mg. Mg equals n divided by cosine theta. Mg sine theta, f of s equals mg sine theta equals n cosine theta times sine theta equals n tangent theta. When the incline, I think that's what I just did. When the incline angle is increased until the block is on the verge of slipping, the force of static friction has reached its maximum value, mu sub s times the normal, mu sub s n. The angle theta in this situation is the critical angle theta c. Let's make these substitutions. Mu sub s times n equals n tangent theta. Therefore, mu sub s equals tangent of the critical angle, tangent theta c. We have shown, as requested, that the coefficient of static friction is related only to the critical angle. Let's finalize this as follows. Once the block starts to move at theta greater than or equal to the critical angle, it accelerates down the incline, and the force of friction is F sub k equals mu sub k times n. If theta is reduced to a value less than the critical angle, it may be possible to find an angle theta prime c such that the block moves down the incline with constant speed as a particle in equilibrium. Again, ax equals 0. In this case, use our equilibrium equations with f sub s replaced by f sub k to find mu sub k equals tangent theta critical, where theta critical is less than theta critical. Okay. Few more slides. A hockey puck on a frozen pond is given an initial speed of 20 meters per second. If the puck always remains on the ice and slides 115 meters before coming to rest, determine the coefficient of kinetic friction between the puck and the ice. Okay, we conceptualize this as follows. Imagine that the puck in the figure slides to the right. The kinetic friction force acts to the left and slows the puck, which eventually comes to rest due to that force. Let's categorize this as follows. The forces acting on the puck are identified in the figure, but the text of the problem provides kinematic variables. Therefore, we categorize the problem in several ways. First, it involves modeling the puck as a particle under a net force in the horizontal direction. The kinetic friction causes the puck to accelerate. The acceleration, remember, is it's slowing down. It's causing it to slow down, and that is an acceleration. The kinetic friction causes the puck to accelerate. You want to say it's causing it to decelerate. There is no acceleration of the puck in the vertical direction, so we use the particle in equilibrium model for that direction. Furthermore, because we model the force of kinetic friction is independent of speed, the acceleration of the puck is constant. So we can also categorize this problem by modeling the puck as a particle under constant acceleration. Okay. Let's analyze this. First, let's find the acceleration algebraically in terms of the coefficient of kinetic friction using Newton's second law. Once we know the acceleration of the puck and the distance it travels, the equations of kinematics can be used to find the numerical value of the coefficient of kinetic friction. Apply the particle under a net force model in the x direction to the puck. So f of x, the sum of the forces in the x direction are the force of kinetic friction and the mass times the acceleration x, acceleration in the x direction. Apply the particle in equilibrium model in the y direction to the puck. F of y equals the normal minus mg equals 0. There is no acceleration in the y direction. Substitute n equals mg and f sub k equals uk times n. Okay, the coefficient of kinetic friction times the normal. The normal is mg, and that's equals the mass times acceleration, the force. So you can see that the m's cancel, and you end up with the acceleration in the x direction equals mu sub k times g. The negative sign means that the acceleration is to the left in the figure, because the velocity of the puck is to the right. The puck is slowing down. The acceleration is independent of the mass of the puck and is constant because we assume mu sub k remains constant. Let's apply the particle under constant acceleration model to the puck. And so this is one of the kinematic equations. V sub x final squared equals V sub x initial squared plus 2ax times the distance. X sub I and is equal to 0. And V sub x final is equal to 0 because it's slowing down to a stop. So we solve for the equation. We solve for the coefficient of kinetic friction, and mu sub k equals Vx I squared over 2g x final. We substitute numerical values. Mu sub k equals 20 meters per second squared divided by 2 times 9.8 times the distance, 115 meters. We get 0.177 is the coefficient of kinetic friction. Let's finalize this. Notice that mu sub k is dimensionless, as it should be. That is, it has a low value consistent with an object sliding on ice. Be interesting to compare what the coefficient of ice is if there is one in the table. Okay, let's look at another. A block of mass M2 on a rough horizontal surface is connected to a ball of mass M1 by a lightweight cord over a lightweight frictionless pulley as shown in the figure. A force of magnitude F at any angle theta with the horizontal is applied to the block as shown, and the block slides to the right. The coefficient of kinetic friction between the block and the surface is mu sub k. Determine the magnitude of the acceleration of the two objects. Okay, we conceptualize this as follows. Imagine what happens is F is applied to the block. Assuming F is large enough to break the block free from static friction, but not large enough to lift the block slides to the right and the ball rises. We categorize this as follows. We can identify the forces and we want an acceleration. So we categorize this problem as one involving two particles under a net force, the ball and the block. Because we assume that the block does not rise into the air due to the applied force, we model the block as a particle in equilibrium in the vertical direction. Okay, let's analyze this as follows. We first draw the force diagrams for the two objects as shown in the figure. Notice that the string exerts a force of magnitude T, the tension, on both objects. The applied force F has x and y components, F cosine theta and F sine theta respectively. Because the two objects are connected, we can equate the magnitudes of the x component of the acceleration of the block and the y component of the acceleration of the ball and call them both acceleration, just the acceleration. Let us assume the motion of the block is to the right. Apply the particle under a net force model to the block in the horizontal direction. So F of x is equal to F cosine theta minus the kinetic friction minus T, and that is equal to M2 acceleration in the x direction equals M2A, because it's the acceleration is the same because we are assuming the string doesn't stretch, or the cord doesn't stretch. Because the block only moves horizontally, apply the particle in equilibrium model to the block in the vertical direction. So the sum of the forces in the y direction is the normal force, n plus F sine theta minus M2G, and that all equals 0. Let's apply the particle under a net force model to the ball in the vertical direction. This is for the ball. The Fy is equal to T minus M1G equals M1A in the y direction equals M1A, because it's the same acceleration as the block since they're tied by the string. Okay, solve the equation for n. Let's solve the equation for n. There we go. N, the n is a normal, equals mg. This is from a couple of equations above. mg2 minus f sine theta. That's the normal. Now let's substitute n into f sub k equals mu sub k of n. So the kinetic friction is equal to the coefficient of kinetic friction times the n that we just solved, m2g minus f sine theta. Now let's substitute f cosine mu sub k times mg. We're substituting into the top equation. Mg minus f sine theta minus m1 times a plus g equals m2a. That comes from the third. The m1 a plus g comes from the third equation. Fy equals t minus m1g equals m1a. Okay, let's solve for a. A equals f cosine theta plus mu sub k sine theta minus m1 plus uk m2 times g divided by m1 plus m2. Now, to finalize, the acceleration of the block can be either to the right or to the left, depending on the sign of the numerator in our result. If the velocity is to the left, we must reverse the sign of the kinetic friction in the first, because the force of kinetic friction must oppose the motion of the block relative to the surface. In this case, the value of A is the same as in our result, with the 2 plus signs in the numerator changed to minus signs. All right, after this ends our lectures on chapter 5, and we'll produce chapter 6 shortly in the future.